Hello everyone, we're in the RBMK simulator. This is a video about an accident. I will simulate what happens when we lose the cooling capability of the condenser. And as you can see, I already have the simulator up and running. So starting from the reactor, we see that we are in auto mode. So the control rods are automatically controlled by this panel. The power set point is at 10%. We have 9.5% of thermal power. The cheat engine is being used to fix the xenon at 123% because we're at such a low neutron flux of 10%. If we don't do so, xenon will increase a lot during the video, and this is not the purpose of this video. Then in the loop 1 and loop 2, in the schematics, if we look here to the left bottom corner, we see that we have one out of the 3 pumps in each loop on. Red is for on, green is for off. So this assures recirculating water through the core of the reactor. Then going further, we'll use the schematics, it's more clear. If we go further from the reactor and the primary loops, we have the drums here, and we have a drum here in the schematic, steam drum flow, a pressure of 9500. This is slightly above what is needed for the turbine to be on grid. And then the water temperature 308 degrees. Okay, we continue going further and we reach the feed water pumps. We see one of the 3 pumps is on, and if we go into this panel, and I can show you that the drum level control is set into the startup valve and 1 element control. Okay, we continue going further. Okay, the radiator is here, but it doesn't matter. Treatment, and these are the water treatment pumps. So one out of the 3 pumps is on, and this pumps the water from the hot well that comes after the condenser. The condenser is fed by one of the 2 pumps, which is on, the other one is off. And this overall, all the system at this moment, it's like in a startup procedure. The turbine is not connected, it's in turning gear. I will just open the dialog 1 second. We see the turbine reset and in turning gear 20 RPMs, but it's not connected. So no steam is going through the turbine at this moment. All the steam is bypassed. You see the main steam dam control is set at 9500. So the valve is open at 17% to relieve the steam pressure in the main steam pipes. Okay, I will close the turbine. We will not use the turbine during this simulation at all. So now what I will do is to turn off this pump, so both pumps will be off. And if you can see, as a thermodynamic system, you don't have any point in which you extract heat from the system. So all the heat being produced in the reactor from the moment we turn off this pump cannot be extracted from the system. Of course, this cannot be sustained at long term, so something will fail. So I will do this now. I will switch off the pump number 1, and we see the flow going down here. Okay, we get the alarm. Condenser water pump trip. Condenser vacuum low, and we see the condenser vacuum that sharply decreased to 0. Because of course we cannot we lost the ability to create condensate because we don't have cooling in the condenser. Okay, for the moment everything is fine except that we got the rupture disk trouble, and some of you may already know this because this is a problem that almost everyone gets when learning the simulator. But it doesn't matter because we don't want to bring this up to power and connect the turbine to the grid. So we will just neglect for the moment this rupture disk trouble. And now what is happening is that this condenser lost the ability to condensate steam that comes from the turbine. And actually in this simulation it's not going through a turbine because I show you the turbine is in turning gear. All this steam is bypassed. So it's going through this channel here and then bypass and then condense it. Because the condenser is not cooled anymore, the steam cannot be condensed, and all the water that we pump with this pump here to the treatment is reducing the level of the hot well. Once the hot well runs out of water, we will see that this pump will trip We'll not have any more water to the treatment system. And if we continue the diagram, we see that the feed water pumps will also run out of water. When this happens, the reactor level will start to decrease because the reactor will not be fed by water. Oh, okay, we also have the two water treatment pumps that pump directly to the system here, but once we get we don't have any more water in the hot well, these pumps will also trip. So at the end we'll have a reactor level decreasing, and when the reactor level is low enough, we will have damage in the channels. How this is called in Russian, but channels refers to the okay, we can call it channels anyway. No, channels are the places where the fuel are stored inside the graphite core of the reactor. I think channels is the K in the RBMK acronym. Reactor P, I'm not really sure, but I'm almost sure in Russian channel it's written in K, so it's this K here. Okay, so everything looks stable now, apart from that we lost the condenser vacuum. So if we wanted to run the turbine with steam, now we will not be able to do so because we don't have vacuum in the condenser, which is the thing that runs the turbine. Okay, just waiting. Power set point still at 10%. And what I'm expecting to see next is a drop in the hot well level. The main steam dam control is still at 17%. I also expect this to increase once we don't feed any more water into the reactor. So the only way to dissipate heat will be to evaporate more and more water inside the reactor. So also to accelerate the decrease of the level inside the reactor. Okay, just waiting for the moment. You see that I have the emergency cooling disconnected and the auto scram control bypassed, so nothing will create a scram. And I want to go till the end to see what happens in this hypothetical case in which we lose the cooling capability in the condenser. This is not a very common drill. Usually what people cares more is the loss of cooling in the primary, so in the recirculating here, in the loop 1 and loop 2, because this can very quickly create a meltdown. If you get a loss of cooling in the condenser, theoretically you are able to press the Z5 button or something like that, the scram button, and stop the reactor, and then you have the emergency of core cooling system, the diesel ECC pump, etc., that can cool down the reactor for 1 day or so until the residual heat of the decay products goes away. But I just wanted to see as an experiment what happens if you don't manage to use these systems like the emergency cooling or the scram, and you lose the condenser cooling. How much time do you have until there is a catastrophic failure in the reactor? Things are still going fine now. I remind you, one out of 3 pumps on in each one of the primary loops. Primary loops in, okay, I call it primary loops. Here they are just called loop 1 and loop 2. These are like the core flow in the boiling water simulator from Acme. So this just recirculates water within the reactor and passing through the drum, but this is always liquid water. So this recirculates water to assure the reactor it's always with liquid water, not with bubbles. If you see in the diagram, this pumps the water that comes from the drum upwards, so this forces the boiling water or the bubbles from boiling water to go up to the drum, and it's in the drum where actually most of the boiling happens, and the steam is created to the main steam line. Okay, things look like still fine. I will slightly increase the power set point so we don't need to wait so long for something to happen, and I will go to 15%. Okay, power set point at 15%, thermal power 14%. And what I plan to do now is to switch off the water treatment pumps. These are these two pumps here, because these two pumps could be pumping water from a external system. If this is true, the reactor could run a very extended period of time without losing the water in it. Okay, now we see reactor level is decreasing. This is because the feed water pumps cannot supply all the water that is being evaporated in the drums, and this is because the water evaporated in the drums is not being condensed. We also see the main steam dam control increase to 40% due to the increase in power set point. And I will just increase a bit more the power set point, maybe to 17%. But I don't want to go to too much above 15%, because I think 15% is the limit after which the feed water pumps cannot catch up with the discharge. So if this happens, that we would not be testing the resilience of the system to a failure of the coolant capability of the condenser, but just the feed water pump capability. So I'm tempted now to turn on a second pump here. So I will open the inlet valve, then turn on the pump, and then the outlet, the discharge valve, just to make sure that we don't have a shortage in the feed water pump systems. Okay, switch on the pump. Okay, it's on, and open the discharge valve. And let's see if this has some influence on the rate of decrease of the reactor level. If so, it means the reactor level was limited by feed water capability, which is not the case, or yes? Yes, we're being limited by feed water pump capability. Okay, reactor level is increasing back. So now we are good with 2 feed water pumps. I will leave it like that, and I will stop the water treatment pumps and condensate storage. I will close the valve and stop the pumps. Okay, and we see the 2 pumps going green here, and it seems these 2 pumps were feeding water from outside the system, even if we don't see in this diagram. This is what I feel. Otherwise, there was heat being produced in the reactor, but all the other systems were stable. Okay, now where we see a decrease in the hot well, but it seems transient. Okay, so as I was saying, as a thermodynamic system, we were generating a lot of heat in the reactor. We're at 16% of thermal power, and there was no heat going out from the system anywhere, except from the ruptured disk. Okay, this could serve as a discharge valve for the steam being released into the atmosphere, and this could alleviate the excess heat in the system. I'm not sure about that. But anyway, I stopped the water treatment pump, so no new water is being fed into the system. So all the water is already in the circuit. And we see the hot well level decreasing now. So now all the water that the reactor needs is fed from the hot well. That's why it's decreasing. We got the alarm low hot well level. Indeed, it's low, and very soon the condensate system pump, this one will trip. As soon as this happens, probably this too will also trip. So just wait. And now I will reduce the power set point to 15%. 17 is a bit too low for the purpose being of this simulation. Sorry, too high. 17 was too high. Okay, hot well level is out of the trend chart. Let's put some music for the waiting. Let's see if I can change the scale here. I don't really know how to change the scale to see what the hot well level. But I think it will not take a long time to trip this pump here. Okay, we got the trip here, hot well level, hot well pump trip. We see the 3 pumps in green, so we don't have any more pumping because there is no water in the hot well. We got another alarm, low the aerator pressure. And very soon I expect the feed water pumps to trip. We also got the aerator level decreasing. And the hot well is increasing back. How is this happening? Where is the water that is filling the hot well coming from? That's crazy. That's crazy. These 3 pumps are off. And I don't see any pump going to the hot well. Let's check the condensate system. Okay, the condensate system is into auto. The aerator flow valve is 100%. I will set it into manual. This doesn't stop the filling. I will go back to auto. The aerator level set point at 0, but it's not at 0. It's going like super high. I really don't know what's going on. The pump chip, that's correct. I will turn off the polishers anyway. There is no flow through them. Okay. We got some alarms. Very low the aerator level. So and now we got the trip. We have the feed water pump trip, and this means now the reactor level will start decreasing. We see some small fluctuation here in the reactor level and also in the reactor activity. Now the reactor is decreasing. I will also decrease power set point to 10%, which was the initial plan of this video. Okay, we're at power set point 10% and the reactor level decreasing very sharply because we are just evaporating water and there is no pump feeding water to the reactor. I remind you the auto scram control is off, so this will continue until we get damage in the channels or the or the fuel rods. We see all the symbols, the radioactivity symbol in green. When there is damage, we will see some change in these symbols. We also got a trip in the recirculation pumps. So now we don't have flow in the reactor anymore, and we have the voiding increasing a lot. We're at 17%, 18%, 19%. There is no flow anymore through the reactor. So all the boiling created in the reactor is generating a positive loop. But luckily we still have control on the control rods, so the neutron flux is still 10%, but the voiding is increasing a lot. We're at 38% voiding, 39, 40% voiding. And it could happen that we lose the controllability of this reactor because we cannot stop the reaction anymore by inserting rods if the voiding increases too much. We're already at 54% of voiding, and the reactor level is very low. It's out of scale. I don't know what's the reactor level at the moment, but it's super low. We could already start having damage in the rods very soon. We have the fuel temperature at 800 degrees. 900, it's increasing very, very quickly in both sides of the reactor. It's 950, 900. It's almost 1960. And we already got damage in most of the fuel channels. You see the symbols, the previous green symbols turned like yellow. And we got high radiation level in containment. It seems the channels are broken. And there are some leakage of radioactive fuel into the containment. The fuel temperature seems that dropped to 300. Is this reading correct? Is this reading correct? 300 degrees? It means that water got into the fuel channels. These are really, this is catastrophic. Oh my god. Look at the neutron rate. It's like crazy. It's out of control. The control rods cannot control it anymore. Look at it. It's just jumping up and down. It's like minus plus 10. We got the alarm of high neutron flux, higher than 8%, of course. Fuel temperature increasing back above 1600 degrees, both sides of the reactor, and look at the oscillation in the neutron rate. This is totally crazy. Control rods cannot control anymore this reactor, but luckily neutron flux is still around 9-10%. So somehow this remains in the average, even if the trend of neutron rate is totally crazy. And look at the drum. The pressure is totally out of control. It's at 18,000 now, 19,000. It's absolutely above of the main steam dam control set point. Temperature of 8,000, this will just vaporize everything. And now you see that the oscillation in the reactor came back to normal, probably because the channels are totally destroyed, and it's quite incredible that neutron flux is still 10%. And I think that this will be the end of this drill, because probably the things don't make sense anymore. The simulator was not designed to go that far in an accident situation, and probably if there was damage in the channels, you will either go into a critical runaway, so neutron flux will go to above 100% and you will have an explosion, or you will go down to 0. But for me it makes no sense that you can still control neutron flux just with the control rods and maintain it at around 9%, even if you have these crazy oscillations here. And what is even less likely is that you reach a pressure like almost twice of the nominal in the drum and things don't blow up, and then down to 0, and temperatures like 10 times higher than nominal, and then down to 300. And this seems to happen in a cyclic way. So because we already got this oscillation, then it stopped, then we got a very high pressure, like now we have 20,000 in the drum. We got some kind of stability in neutron rate, and I identify at least this pattern. So yes, I think we reached the technological limit of the simulator. We cannot simulate such a behavior with the simulator. We are getting some cyclic, meaningless behavior, and yeah, I hope you enjoyed this video, and if you have some ideas from other transient or accidents, just tell me. See you, bye.